no real physics, intuition explained behind it. And in terms of experimentation, we saw an acceptable controlled release mechanism, which was nice. And but yeah, we were unable to determine their exact, due to lack of the presentation, which we weren't able to determine how exactly they were changing variables, how exactly their theory matched their results. There was no explanation of the setup except for just an animation and a preliminary demonstration at the start. So they didn't explain how they control variables, for example, and which ones they changed. They only got like two. We don't know how the results were recorded, and so it's really hard to kind of criticize what they had. And so with results, there was again good animation, and it seemed comparisons with parametric plots we will bring up in the discussion. In terms of areas for improvement, obviously time management issue. There's no results or comparisons there analysis presented. No comparison to there was no theory. The theoretical models from their model were not presented, and ultimately the problem statement was obviously not fulfilled from what we heard. There was just a parametric plot at the end, and I'd like to use the time to bring into discussion. So the points for discussion I'd like to cover are the frictional interaction and qualitative explanation of the looping pendulum, a definition of what it requires in physics understanding, force diagrams, and then phases of the problem solved. And we think this is really important. This is the main thing. This is the actual phenomenon. Assumptions of their model, and of course, the results they got and how closely they match. So firstly, I'd like to ask the reporter. We'll start with the second point. The qualitative explanation of the looping pendulum.
Okay, so
can you describe the pendulum phenomenon, the looping pendulum?
Okay, as I explained at the beginning, the qualitative explanation. As we release the rod and it sweeps around the rod, it decreases the friction around the rod, and thus the lighter rod can stop the heavier rod from falling. And then
are you able to draw, for example, a force diagram with where happened?
Okay, I can show you on the slide.
Yes, or I can draw a force diagram.
Here is the force acting on the system. There is also
there's no gravitation
force acting on here and here.
Mm-hmm.
They are represented in the equation.
And could you kind of qualitatively explain where
those forces are acting on those rods?
Could you explain when the looping pendulum phenomenon occurs and what it looks like?
Okay, so when the friction, the friction around this rod can increase the amount of.
Okay, so essentially, I think what might be important here is to first look at this is a heavier mass, this is a lighter mass, and so this has a weight force down, this has a weight force down as well. The heavier mass is going to pull down initially as the lighter mass is released, and this is going to, the heavier mass is going to fall straight down, but the lighter mass is going to have some component of vertical acceleration downwards, but also tangential towards the roll, and that is what is going to make it loop around. And if enough energy essentially is imparted to the smaller mass, it gains enough of an angular velocity such that it can loop around. And that is what perhaps could have been a really good intuitive explanation of what's happening. And which we found was
the rod is accelerating and this binding angle.
Yes, it does.
So they also asked me your questions. How did we measure the coefficient of friction? I think we can talk about this right now.
We'll get to friction later if that's fine. Can we discuss first the phases of the phenomenon?
Okay.
So what phases did you observe in the phenomenon?
Okay, first we can divide between the static and kinetic friction.
Yes.
There are different phases. And
so when kinetic friction is interacting, the bigger mass is obviously moving, and then as it stops, it now starts interacting with static friction. Is that correct?
When it stops, then there is static friction, right?
Yeah. And so with these phases, now can we go back to an image of, not an image, an image of your animation, please?
Okay, which one?
Could you explain what were the assumptions of the model that you use? So the equations you have, the differential equations you create.
Okay, so as I said, the model is in 2D, so there is no movement in the.
So what are the assumptions in your model?
The movement is in 2D, so there is no. The loads are moving in one surface.
Why, for example, did you not consider a 3D one? Because obviously in reality you would see the looping wouldn't go through the string itself, so it has to have a C-axis component of the looping. So
we didn't include those in our investigation, but also we didn't do experiments that were showing.
It's fine, just explain it. That's fine. But it's like,
Thank you. So there are different regimes also where, for example, here, where the rope was moving around the rod, and we throw away those experiments because of this movement that it would be not adequate for the physicist.
Okay. If we look at even that image, obviously we see that the center of rotation of the smaller mass is changing as the smaller mass loops around. Did you incorporate that as an assumption?
Changes?
So the center of rotation, so that pivot point at which the string detaches from your rod.
The equation of motion include that.
Did you describe? Okay.
Yeah.
And did you have results that?
We described the position of the x and y position of the lobe with the.
So did you have a changing pivot point for the smaller mass? In the
No,
simulation?
it was
So
described by the length of the whole string, by the winding angle, and by the. So basically, when you know the winding angle and when you know the distance from the length of the rope of the lighter lobe's side, you know the position of the lighter lobe, and that's the way we determine it.
I'm just saying, do you agree that the point of contact with the rod changes as the smaller mass moves around? Was that in your simulation?
Yes.
So it was
Our equations were including this.
And so
this
did your data have match what you expected for
do you want
cases where
the comparison?
Yes.
Right. Okay, I can show you the comparison.
Well, did it match with what you expected? And if not, then why? Or if so, then why?
Okay, it did. Actually, in our situation there was one kind of a problem. We just sit here, and there is the movement here that is wasn't predicted by our simulation, and we think that this movement is due to the extensibility of the spring. But in our further experiments, we derive from the tracker, from tracking the movement of the lighter lobe, the velocity and the position of the lighter lobe, and after sometime after the releasing, and we
tracker, is that right? So
yeah we try.
Was there uncertainties when you tracked it, or errors? Uncertainties when you tracked?
They are, I think, in the range of the points here or.
So you have included uncertainty bars, or you haven't?
I haven't, but. Yeah.
Okay, so there was lack of error analysis, which would have added to the accuracy, the validity of your results. So can we? One second, sorry. So again, can we go back to the assumptions behind your equations?
What do you mean about that?
So for example, did you have a length? Did you look at the elasticity of the string, for example? So if we go back to the figure to show, there was.
So we neglected it, and we had experiments made it. We made an experiment that proved it, but due to the initial over-tension of the lighter lobe, of the.
So was the string elastic, or?
It was only a little bit, and it was affecting the
what
phenomenon
effect
only at the beginning of the phenomenon.
What effect was that? What effect was that of the?
This was this effect, which we got rid of by tracing the movement of the lighter lobe. And for example, we evaluated the velocity here of the lighter lobe and the position, and from this point we ran a simulation.
Can you physically explain what was happening at that discrepancy and why it was
as I already did also. So at the beginning, if you want to hold the lighter, heavier load with the lighter mass, and there is a low winding angle, then the tension on the part with the lighter load have to decrease when we release it. Because at the beginning. Okay, so
also, could you explain, for example, the discrepancy you see You obviously said you didn't put error bars, but you see it's not exactly matching. So
Okay,
what could we do for that?
Also, I think that I avoid the error bars. The 1 pixel on the tracker was 0.2 millimeter, so that would be the error bars. But here, as I mentioned in the beginning of our presentation, we think that the coefficient of friction was a very important factor in this situation.